So we talked about this reaction before. 3 oxygen molecules is in equilibrium with 2 ozone molecules. Why, which is good for us, is the equilibrium so far over to the left? What drives it? There's 2 things that drive equilibrium. Okay, like which way they're going to go. We look at enthalpy and entropy. So, everything in nature wants to be stable, wants to be more stable, wants to be like happy and stable, right? So if you throw sodium in water, everybody's seen that reaction, right? Starts to ignite, produces hydrogen gas. Why does it happen? You don't have to do anything to it. You just throw it in the water and it reacts, right? It's because the sodium is more stable in the water, all right? You're reaching a more stable state, all right? It's an exothermic reaction. If you remember exothermic reactions, you end up at a lower energy state, right? Because you're giving off energy, you're more stable, all right? So that is one thing that drives reactions, is the enthalpy of the reaction. And enthalpy is just PE, potential energy, not physical education. The lower the potential energy, the more stable something is. So on a potential energy diagram, the lower you are, the more stable. That's why exothermic reactions, we tend to say, especially in grade 11, we said that they were spontaneous reactions, okay, because you're going to a lower energy state, all right? And if you remember, I think in the first unit, we talked about delta H. H is the symbol for enthalpy. It's the enthalpy of the products minus the enthalpy of the reactants. If it's less than 0, that's exothermic. So we want delta H to be negative. That's the ideal. All right. So in a chemical reaction, nature favors decide with maximum stability. Which means minimum enthalpy. We want delta H to be negative. That's what's going to push a reaction one way or the other. Okay? That's only one thing that'll drive a reaction, though. The other thing is entropy. All right? Entropy measures the randomness of something, of a system. All right? Everything wants to be random. The more random, the better. If you take just water and food coloring, what happens if I put it in here? Does it just stay as a blob? No. It's going to start mixing. If you left it overnight, it would all be blue. We don't have to do anything to it. All right? The water molecules have kinetic energy. They're going to increase the randomness. When it mixes up, it's more random and it's more stable. Okay? Now, you can get it back out. You can reverse that process, but it's not easy. What do you have to do? You have to boil off all the water, right? And then collect it. Collect the food coloring or boil off the food coloring. I don't know what the boiling point of either is. But anyway, it would take a lot of energy to do that. Okay? Everything in the world wants to be more random. Okay? So chemists came up with a way of measuring randomness. They gave it the symbol S. That makes perfect sense. Okay? So when a system has a lot of randomness, in other words, a gas is more random than a solid or a liquid. Those are more organized, especially if you think of a solid, you have a crystal structure, everything's very organized. Okay? Gases are just kind of floating around all over the place. That's a large entropy. All right? So then because We want to know what the delta S is, the change in entropy. Entropy of the products minus entropy of the reactants. The world wants positive entropy. Okay? That's what we want. Because that means you have more randomness. The degree of randomness in the products is bigger than that of the reactants. That would give us a delta S that's positive. That's what we want. Okay? So this is where kids will get confused. Delta H we want to be negative because that means we have a more stable product. But entropy we want to be positive because that means we're more random. So ideally we have an exothermic that produces a highly random product. That'll push the reaction towards, I guess, to the products. Okay? We're going to practice this because it's very, very important. It drives a lot of stuff. So, in a chemical reaction, nature favors the side with maximum entropy. So, gas is greater than solutions. When I say solutions, I'm talking about aqueous, so something dissolving in water. And then it's is greater than liquids, is greater than solids. Solids are the least random, which kind of makes sense. Okay, we'll just do the next table, and then that's all we'll get through today, and then we'll finish it off tomorrow. So, here we go. 4 different cases that we need to understand. If the products are more stable, okay? So if products are more stable, if you think of the enthalpy diagram, that looks like that, right? Which is what type of reaction? That's an exothermic reaction, which means delta H is negative. So delta H is negative. Okay. And then we say the products are also more random. If they're more random, delta S is positive. Okay. So if you have the reaction that is more stable on this side, products are more stable, and they're more random, everything is pushing the reaction this way. Okay? Does that make sense? Right? Everything wants to be more, like, look at the water right now. I didn't do anything to it, and it's basically all just mixed. Right? Like, it just happens naturally. Okay? So everything gets pushed this way. Because delta H is saying, I want to go this way because I'm more stable. And then the randomness is saying, it's more stable over here, so we're going this way. So the products are favored. Due to delta H and delta S. Therefore, equilibrium is shifted to the which way? To the right. So that means we're going to have more products than we are reactants. Okay. What if the products are less stable? Then that is that type of potential energy diagram, which is what type of reaction? Endothermic reaction. So delta H is positive. And the products are less random. So delta S is negative. Okay. So which side is being favored? Reactants. Therefore, the equilibrium is shifted to the left. So the left side of the reaction is favored. It's not going to be easy to get the reaction to go this way because all the forces of nature are pushing back that way. All right? So you would have to, that's why it's an endothermic reaction. You'd probably have to put a ton of energy into it to push it in that direction. Okay? And there's other things you can do as well that we'll learn, but it's not easy. These are the two extreme cases. They either both favor the products or they both favor the reactants. The reality is most stuff is somewhere in the middle. Okay? So, what if you have the products are more stable? Endo or exo? Exo. Okay. So it's an exothermic reaction. That's delta H. So delta H is negative. But the products are also less random. So that means delta S is negative. So what do you get then? You got delta H pushing you this way, and you got delta S pushing you back the other way. So you get some sort of equilibrium. It's going to depend on which force is stronger. Okay? So opposing forces. Therefore, equilibrium will be, I don't know. I'll just say in the middle, and I'll put that in quotes. Actual position will depend on the strengths of enthalpy and entropy. Of H and S, enthalpy and entropy. Okay. So you'll be somewhere in the middle. Now, how far to the left and right? Are you slightly to the right? Are you slightly to the left? Is going to be dependent on the individual reaction. And then the final one, last thing we'll do today, if the products are less stable, that's an endothermic reaction, sorry. So delta H is positive. Products are more random. Delta S is positive. It's going to be the same as above. You'll be somewhere in the middle that's going to change depending on the reaction. Yes? I can't hear you, sorry. It wouldn't look like that. That's a so I guess you could have. I'll look what So delta S, we'll learn how to determine that tomorrow. Normally we'd lead right into it right now, but basically you can look at a reaction and depending on the phases and the number of molecules, we can determine whether delta S is going to favor the products or the reactants. That's tomorrow's lesson. But there's only 4 minutes of class left, so we'll stop there. Remember, your labs are due on Friday, peoples.